Welcome back, friends. So next property what we are going to see is the differentiation in time domain. So differentiation property. What is differentiation property saying that? Suppose a signal x of t having Fourier transform x of omega, then what is the Fourier transform of dx of t by dt? So this is nothing but j omega multiple. We have to simply multiply j omega for the Fourier transform. Suppose if I differentiate n times d square x of t by dt square, then this is going to be let's say 2 times, then we have to multiply 2 times j omega. If I differentiate like n times, then we have to multiply j omega like n times. Okay, so this is the way differentiation property can be applied. So to apply differentiation property, so let's say the signal, how we can apply this differentiation property to calculate the Fourier transform. Let's see one signal what we have. Please take it. So let's give an example. Fourier transform of symmetrical rectangular pulse. Rectangular pulse. For this signal, we have to calculate the Fourier transform. What do you mean by symmetrical rectangular pulse? This is what the symmetrical rectangular pulse. So it is symmetrically located with respect to y-axis. That means how much distance from x-axis this side, it has to be same. So let's say minus t by 2 plus t by 2. Let's say height a. If I ask what is the width of this rectangular pulse, that is nothing but capital T. So this is what the signal x of t is given. For this signal, we have to calculate Fourier transform. How we can do that? So let's say I will go in both the methods. Two methods we have. So direct formula method, method 1. Direct formula. What do I mean by that? Suppose x of omega is equal to integral minus infinity to infinity x of t e power minus j omega t dt. This is the formula we have to use. But I don't have to worry about minus infinity to infinity. I just have to take the integral from minus t by 2 to plus t by 2. So this can be written as minus t by 2 to plus t by 2. X of t value is equal to a e power minus j omega t dt. So if I do integration, then this is going to be a e power minus j omega t by minus j omega minus t by 2 plus t by 2. because of the minus sign, so I can take a by j omega. Because of the minus sign, first I can substitute the lower limit, then this is going to be e power j t by 2 omega minus e power minus j t by 2 omega. So if I multiply with 2 and divide with 2, then this is going to be written like this: e power j t by 2 omega minus e power minus j t by 2 omega by 2j. Can I write like this or not? So 2 get cancelled, j comes here, so this is what we are going to get. And I know this factor, this is nothing but sine t by 2 omega, so this is going to be 2a by omega sine t by 2 omega, sine t by 2 omega. So here I want to write this function sine t by 2 by omega, sine t by 2 omega by omega into sampling function. I can write like this. So 2a t by 2 sampling t by 2 omega. 2 get cancelled, finally we are left with at sampling t by 2 omega. So this is what x of omega. This is what x of omega. Clear? Take it. And in method 2 also the same way we can go. Let's see method 2, that is differentiation method. Differentiation method. If I say for this x of t signal, if I do the differentiation, then we are going to get one impulse function at minus t by 2, one impulse function in the downward direction at t by 2. So if I calculate first dx of t by dt, then how it look like? At minus t by 2, at t by 2, we are having two impulse functions. At t by 2, minus t by 2. Minus t by 2, we are having upward impulse function with amplitude a minus a. Then we can write dx of t by dt is equal to, we are having two impulse function, a delta t plus t by 2 minus a delta t minus t by 2. In this way we can write. Now if I calculate the Fourier transform on both sides, by applying Fourier transform on both sides, then what we are going to get? J omega into x of omega is equal to a. For delta t, it is nothing but 1. What about delta t plus t by 2? This is going to be e power j t by 2 omega minus e power, sorry, a is there, a e power minus j t by 2 omega. This is the way we can get. So what is x of omega? We are going to get a by j omega e power j t by 2 omega minus e power minus j t by 2 omega. So after this, so from this, so here it is going to be the same thing. Again we have to go for the same simplification. Finally we are going to get this answer only. So if you observe carefully, so up to this one, a by j omega e power j t by 2 omega minus e power j t by 2 omega. So after that it is going to be same. So finally we are going to get this one only. So I hope you understood. So we can apply differentiation method or we can apply direct formula method. Whatever the method, finally answer has to be the same. I hope you understood. So I am not doing the rest here. So because from here this is going to be continuing. These steps are going to be continuing. Okay. If you want you can take it again. So finally you are going to get this one. First take this one, then I will tell you how to remember this easily. Okay. Take it. Okay. I hope you have completed. So finally we have to remember direct formula. So This is the formula what we got. For this function x of t, what is x of omega we got? X of omega is equal to at sampling t by 2 omega. This is what we have to remember. So if I say this can be remembered in a easy manner, what is that? First you have to understand what is a multiplied with t. If I take what is the width of the signal, width of the signal is nothing but t, height of the signal is nothing but a. Then what is a multiplied with t represent is nothing but area under this rectangular pulse, area under this rectangular pulse only. So I can write this at is nothing but area under rectangular pulse, or simply area. Next, what is this t by 2 indicate? Which is nothing but width by 2, that is nothing but half of the width. So that's what. So in general I can write like this. This is area sampling width by 2 into omega. So this is a general form you have to remember about x of omega. X of omega, area multiplied with sampling width by 2 omega. This is the way we can remember. Next, if I want to calculate x of f, because in communication mostly we will deal with f notation. So x of f, so let's see what is x of f. I told you x of f means omega has to be replaced with 2 pi f. Then this is nothing but at sampling t by 2 into 2 pi f, 2 pi f. 2 get cancelled, 2 get cancelled. Finally what we are left with, at sampling pi tf, 2 get cancelled, pi tf. And we know sampling pi something can be written in terms of sinc function. So finally what we got, x of f is nothing but at sinc tf, sinc tf. Now I want to write in more general way. So what we can write, x of f is equal to at represent area and t represent width. So directly we can write x of f is equal to area multiplied with sinc function, sinc. So instead of taking width by 2 here, we have to take directly width only, width into f, width into f. So this is what the x of f. This is what x of f. So I hope you understood. X of omega means we have to consider the sampling function. X of f means we have to consider the sinc function. But here in x of omega we will take width by 2, but in x of f we will take width. So you have to remember this. X of omega is equal to area sampling width by 2 omega, whereas x of f is equal to area sinc width into f. So that's what we have to remember. Take it. Simply do this. What is x of omega, what is x of f for this function? So directly let's see, because it is symmetrically located, rectangular pulse. X of omega is equal to area. What is the area? Width is nothing but 12. 12 into 2, that is nothing but 24. 24 sampling width by 2, that is nothing but 6 omega. So this is what the function x of omega. How we can write x of f? Again, area 24 sync. What is the width? 12 f. 12 f. So I hope you understood. So here it is nothing but width by 2. Here it is directly width. So this is the difference between x of omega and x of f. Clear? Take it. Which is like this. -1, 0, 5, let's say 4, x of t. For this function, I have to calculate what is x of omega. But if you observe carefully, the given x of t signal is not symmetrically located. And we have derived the formulas only for symmetrically located rectangular pulse. But it is not a symmetrically located rectangular pulse. Then what we have to do? So assume a signal y of t. Assume a signal y of t. Let y of t signal, which looks like this, let's say. Suppose if it is symmetrically located, you tell me from where to where it has to locate. So first you have to understand what is the width of the signal. -1 to 5, that is nothing but 6 is the width. If 6 is the width, half width this side, half width this side. So if it is a symmetrically located, it has to be from -3 to +3. So it has to be from -3 to +3. -3, 0, +3. So let's say 4. Now you tell me what is y of omega for this signal? Because it is a symmetrically located, we can directly say what is y of omega. What is y of omega? Which is nothing but 6 into 4, 24. Sampling 3 omega. So this is what y of omega. But we have to calculate x of omega. How we can do that? First, if you understand what is the relation between y of t and x of t, that means what we have to do with y of t so that I can get x of t. Suppose if I see, if I take y of t and delay the signal by 2 units, if I delay the signal by 2 units, can I get x of t or not? Yes, definitely I am going to get x of t. So by delaying y of t, I am going to get x of t. So I can write the relation between x of t and y of t as like this. I can write x of t is equal to y of t minus 2. By delaying 2 seconds, I can get x of t. Now, if I take Fourier transform on both sides, then what is x of omega is going to be? Which is nothing but y of omega e power minus j 2 omega. E power minus j 2 omega. So this is what x of omega. So we already got y of omega. Simply we have to multiply with e power minus j 2 omega. This is nothing but 24 sampling 3 omega e power minus j 2 omega. Time shifting property. I hope you understood. Okay, this is what x of omega. So just understand this one. X of t is not symmetrically located. For that, we are assuming a function y of t which is symmetrically located. Then we have to see what is the relation between y of t and x of t. So from that we came to know x of t is nothing but y of t minus 2. So we know y of t, what is the y of omega. Now for y of t minus 2, just we have to apply the time shifting property. So in the time shifting property, this is nothing but we have to multiply with e power minus j 2 omega. Clear? Take it and calculate that. So let's see. So Fourier transform of symmetrical triangular pulse. Symmetrical triangular pulse. That means so let's call it as x of t, symmetrically located triangular pulse. So it is existing from minus t by 2 to t by 2. So still the width of the signal is nothing but t only. So here amplitude peak value is equal to a. Now how to calculate the Fourier transform for this signal? So for that I will go for 2 times differentiation. Let's say dx of t by dt. How it will look like? If I differentiate it, what is the slope of this curve? A divided by t by 2, that is nothing but 2a by t. So from minus t by 2 to 0, minus t by 2 to 0, we are having the value is equal to 2a by t. Next, from 0 to t by 2, which is nothing but minus, so negative value for that. T by 2 up to t by 2, what is the value? Minus 2a by t, minus 2a by t. So for this again if I do the differentiation, d square x of t by dt square, then what will happen? So if you observe carefully, we are having 3 impulses. One is at minus t by 2 in the upward direction, one is at 0 in the downward direction, one is at t by 2 which is also in the upward direction. So if I say minus t by 2 at t by 2 and 0, we are having the impulses. So what are the impulses? Let's see. At minus t by 2, we are having in the upward direction impulse function. What is the strength of this function? 2a by t, that is the jump value. And at t by 2 also we are having in the upward impulse function, that is also 2a by t only. But at 0 we are having the downward direction impulse function with the strength is equal to minus 4a by t, minus 4a by t. So these are the 3 impulse functions what we have. So I can write d square x of t by dt square, d square x of t by dt square in the form of impulse functions. What is that? First I will take these 2 impulses. So this is nothing but 2a by t delta t plus t by 2 minus plus 2a by t delta t minus t by 2. These 2 impulse functions I have taken, and here in the downward direction we have impulse function at 0 minus 4a by t delta t, 4a by t delta t. For this if I write Fourier transform on both sides, if I take Fourier transform on both sides, so you tell me Fourier transform of this one, this is nothing but j omega whole square x of omega is equal to, if I take 2a by t common out, then this is going to be e power j t by 2 omega plus e power j minus j t by 2 omega. If I take 2a by t, for this function e power j t by 2 omega, for this function e power minus j t by 2 omega, minus 4a by t, minus 4a by t. Next, that implies this is going to be minus omega square x of omega, minus omega square x of omega is equal to So if I multiply with 2 and divide with 2, so this is going to be 4a by t. If I divide with 2, this is going to be cos t by 2 omega minus 4a by t. 4a by t. So take this minus here, then this is going to be here, this is going to be here. So finally, what is x of omega we are going to get? So 4a by t if I take common into omega square multiplied with omega square. This is going to be 1 minus cos t by 2 omega. Cos t by 2 omega. And we know 4a by t omega square. 1 minus cos theta can be written as 2 sin square theta. 2 sin square theta by 2. So it is going to be 2 sin square t by 4 omega. 1 minus cos theta is equal to 2 sin square theta by 2. So that's what we are going to get. So it is going to be 8a by t. Then this is a sin square or sin t by 4 omega by omega whole square we can write. Bring this omega square here. So this is what we are going to get. Now that is equal to 8a by t by 4 sampling t by 4 omega square. So 8a by t square by 16 into sampling square t by 4 omega. So this is going to be half a t sampling square t by 4 omega. So this is what we are getting finally, x of omega. First you can take this x of omega value. First take the derivation, then I will tell you how to remember this one in a very easy manner. Okay, let's take it first. Finally you don't have to remember this derivation, so you have to remember only the final result, and how to remember this final result also I will tell you. First take it. So finally x of omega value what we got for this function is, I will write like this, half t a sampling t by 4 omega, sampling square actually, sampling square. Now if you observe carefully, half t is nothing but base, a is nothing but height. So is it nothing but area under this triangular function? Area. Next, sampling square. T by 4, width is nothing but t, so t by 4 is nothing but width by 4, width by 4 omega, width by 4 omega. So this is what x of omega we are going to get. X of omega. But I want to go for x of f. So if I say x of f, let's see, x of f. Omega can be written as 2 pi f. So 2 times goes. So width by 2 pi f. So that pi f can be written as a sinc function. So area sinc square width by 2 into f, width by 2 into f. So this is the way we can write. So finally you have to remember directly. For triangular function we are going to get a sampling square function, and here area, here it is width by 4, but in x of f area width by 2. So I hope you understood. For a rectangular function we are going to get a sampling function, but if it is a triangular function it is going to be sampling square function. That's only the difference between them. Okay, take it. Okay. For this function, we have to calculate x of omega. Again, if you observe carefully, so it is not a symmetrically located one. What if I take, let y of t, the signal y of t, which is symmetrically located triangular pulse. So if it is a symmetrically located, if you observe carefully, -2 to 6, we are having 8 units. So if it is 8 seconds, if it has to be symmetrically located, then it has to start from -4 to +4. So let's say it is starting from -4 to +4. -4, 0, +4. So it is 12. So for this, we can write y of omega. What is y of omega? Half base 8 into height 12. Sampling square. Width by 4. So what is the width here? 8 by 4. There is nothing but 2 omega. 2 omega. So finally, 48 sampling square 2 omega. So this is what y of omega, but we have to know what is x of t. So what we have to do with y of t, so that I can get x of t, I have to delay by 2 units. So that means x of t and y of t having a relation which is x of t is equal to y of t minus 2. So from this, what is x of omega? Which is y of omega e power minus j 2 omega. So simply we got y of omega that has to be multiplied with e power minus j 2 omega. So 48 sampling square 2 omega into e power minus j 2 omega. So this is what the Fourier transform for x of omega. Clear? Take it. Okay. So let's see the next property, frequency shifting property. Frequency shifting property. Let's say a signal x of t having Fourier transform x of omega. Now, if x of t signal is multiplied with e power j omega naught t, then the Fourier transform will be x of omega minus omega naught. If you observe carefully, here frequency is getting shifted. In time domain, we have to multiply with exponential. That's what we have seen in the time domain also, or time shifting property also. So exponential multiplication in one domain leads to shifting in another domain, or we can say shifting in one domain leads to exponential multiplication in another domain. So if I do shifting in the time domain, in the frequency domain we have to multiply with exponential, or if I do the shifting in the frequency domain, in the time domain we have to multiply with exponential. So this is the thing you have to remember. Shifting in one domain leads to exponential multiplication in other domain. So what is that domain? You can understand. Suppose if it is a time domain, shifting in frequency domain, it is exponential multiplication. In the frequency domain, if it is shifting, then in time domain, it has to be exponential multiplication. That's what the thing you have to remember. So in the similar way, we can write x of t is multiplied with e power minus j omega naught t. Then this is going to be x of omega plus omega naught. Omega plus omega naught. Let's take small examples so that we can understand easily. Let's say delta t having 1. What if I take 1? What is the Fourier transform for 1? We have seen 2 pi delta omega. 2 pi delta omega. Or in the f domain, we are having delta f. Simply delta f. Now, if I multiply with e power j omega naught t, if 1 is multiplied with e power j omega naught t, that is going to be e power j omega naught t. So this is going to be 2 pi delta omega minus omega naught. We can write this e power j omega naught t as 2 pi f naught t. Then or we can write delta f minus f naught. Delta f minus f naught. Okay. So I hope you understood what I am trying to say. So in this case, these cases can be written like this also. Suppose x of t having x of f, then x of t is multiplied with e power plus j 2 pi f naught t. Then we are going to get x of f minus f naught. In the similar way, if x of t is multiplied with e power minus j 2 pi f naught t, then this is x of f plus f naught. F plus f naught. So that's what I am telling you. Okay. So for the timing, just make it as a x of omega only. X of omega. So this is what we get. E power, let's say minus j omega naught t. Then this is going to be 2 pi delta omega plus omega naught. Omega plus omega naught. So from this, if I write what is cos omega naught t? Cos omega naught t. Cos omega naught t can be written like this also. E power j omega naught t plus e power minus j omega naught t by 2. For this, if I calculate the Fourier transform, for this one we are going to get 2 pi delta omega minus omega naught by 2, that is nothing but pi. So if I take pi common out, then we are left with delta omega minus omega naught plus delta omega plus omega naught. So this is what the Fourier transform we are going to get. So in the similar way, in f domain, cos 2 pi f naught t can be written as e power j 2 pi f naught t plus e power minus j 2 pi f naught t by 2. So for this, what is x of f? What is x of f? For this function delta f minus f naught, for this function delta f plus f naught, so 1 by 2 delta f minus f naught plus delta f plus f naught. So this is what x of f we got. X of f. Okay. So if I draw what is x of f, how it look like with respect to frequency. With respect to frequency. Then we are having two impulse functions. One is at f naught, another one is at minus f naught. So here at minus f naught with 1 by 2 amplitude, and at f naught we are having 1 by 2. So from this, what we got understood is cos 2 pi f naught t having only one frequency, which is nothing but f naught. That's what the meaning of it. You may get doubt, sir, it is having two frequencies, one is minus f naught and another one is f naught. No, it is having only single frequency, which is nothing but f naught. Because what are the frequency components if it is containing? That means we have to see only the positive frequencies. So in that case, So we are having only one positive frequency, which is nothing but f0. And what is the amplitude? So in that case, we have to take 1 by 2 plus 1 by 2, which is nothing but 1. So at a frequency f0, we are having an amplitude of 1. So that's what the meaning of it here. Suppose if I take a here, then we have to write here a by 2, a by 2. I hope you understood. Take it.